All right, so aside from what's up here so far, what can you all tell me about continuity, what you remember of it?
There's no breaks from holding the graph.
Yeah, it's basically the idea that you can draw your graph without ever lifting your pen or pencil, right? And generally when we talk about continuity and discontinuity, continuity we talk about in terms of intervals, right? Because we talk about this chunk being continuous. In discontinuity, we generally talk about in terms of a single point. Like our function is discontinuous at a point, right? Because it doesn't make sense to talk about something that happens at one point in terms of an interval, right? Like, okay, sure, one might be where our function is discontinuous. We're not going to say that our function is discontinuous between 0 and 2. We're just going to say that it's discontinuous at 1, right? Because why make that difference, right? Like, why make that argument? So, having said that, the basic ideas of what it means to be continuous, it just requires that first, our function is defined as c. Now this sets us up for a particular type of discontinuity. Right, we could have something like this occur if we just went with that first definition. Agreed? The second definition, if we just went with that, or the second part of the definition, we would like something like this. Right? If all we cared about was our second definition, well, we could have a discontinuity that would look like this. Does everybody agree? So the reason for this third is that it says the first one allows for this type of discontinuity to occur. The second one allows for this type of discontinuity to occur. But if we demand that the limit as x approaches c for our function to be equal to f at c, then we get rid of both possible cases, right? Does that make sense what it means? Yeah. Having said that, like I said, the idea is really that we just want to be able to say we can draw our graph without ever lifting up our pencil. This is like an intuitive understanding of what it means. As a couple quick examples, we have the traditional discontinuity, right? Where our graph is just discontinuous, like it is in this case. Our function doesn't have a value at c, and the limit exists. That's what this is. This is the case, like we've got up here, where our function exists at c, but it's a different value than what our limit is. Agreed? And then we have what's called a jump discontinuity. In this case, our function exists at c, but the limit from the left and the limit from the right don't agree, so the limit doesn't exist. Does everybody see what I mean? So together, the three rules basically says, in conjunction, the limit exists here. The limit exists here, but isn't equal to this. The function exists here, but the limit doesn't exist. All three of our rules put together gets us around all of these different possible problems. So that's why we have all three of them. Everybody with me so far? So it might be useful then to know what type of functions are continuous, where and when. Well, polynomial, it's always going to be continuous. However, a rational function, it won't necessarily. A rational function is only continuous for numbers in its domain. So these are all polynomials. Naturally, they're going to be continuous, right? We've got x squared minus 2x plus 3. And we've got x cubed minus x. All of these are polynomials. So they're always continuous. We can see that in their graphs. In this case, we've got a bunch of rational functions. We've got 1 over x, x squared minus 1 divided by x minus 1. And then we've got 1 over x squared plus 1. And we already looked at these last class, so we already know that none of these are minus 8. The first two have discontinuities, but the last one is continuous everywhere, right? So, before I go on, this first graph here, 1 over x, this is an example of another jump discontinuity. The reason why we call it a jump discontinuity is because, well, there's a huge jump, right? Our limit from the left, as x approaches 0, is going to be negative infinity. From the right, it's going to be infinity. So there's literally an infinity of numbers you have to jump between. So how would you choose what your limit should be, right? That's why we say again that this is discontinuous, and the limit doesn't exist. So sometimes it's useful to reduce what we're looking at, right? You can just say, I know I have this function and it might exist for all real numbers, right? Like I could look at all of these different possible values from negative infinity to infinity. But I want to zoom in on just what happens between A and B. When we do that, we want to look at what the continuity is at the boundaries of that. We have to use the one-sided limits. Does that make sense what it means? So what I am saying is this. Maybe we have a function that looks something like this. And we say, all right, we want to truncate what we're looking at. We just want to look from A to B. Right? We can choose to reduce our interval. In that case, to look at the limit from A to B, at A, you would have to use the right-hand limit. At B, we'd have to use the left limit. Because we reduced all the possible values that we're looking at, right? It's kind of like saying, we don't care about that part. We don't care about that part. We only want to know what happens inside this window. Is everybody cool with that? I said that. All right. So how about this? What's the domain of this function first? How about I give you all a minute to work on that? See if you can come up with the domain and figure out where it's continuous and discontinuous at. So, for this problem, the first thing we might want to do is look for the domain of our function. Because our function is the square root of a thing, we just need to know when that thing is less than 0, right? And we can throw that part out. Does that make sense what I mean? Which is the same thing as saying, what part of that thing, when is that going to be greater than or equal to 0? From that, we get that the domain of our function is going to be from negative infinity to 3, including 3, right? Is everybody cool with this? So, what then can we say about the continuity of this function?
It's continuous on the domain.
Yeah, it's continuous on its entire domain, right? Because its domain is the interval from negative infinity to 3. We know a limit would kind of exist in the left-hand side of the limit as x approaches negative infinity, right? So what I'm saying is, in the sense that this thing happens, we can kind of say it's continuous, right? Towards infinity. And in the sense that the limit as x approaches 3, I'll run that backwards. So I wrote that backwards, right? It's supposed to be the right-hand limit. This was supposed to be the left-hand limit. Because we're coming at 3 from the left. We're getting at negative infinity from the right. So the left-hand limit of f of x as x approaches 3 from the left is going to be 0. So we'll never actually be able to get to infinity, but if we could, to negative infinity, but if we could, it's reasonable to say that that limit or that function would be infinity there, right? Does everybody agree with what I mean? And our function here is equal to its limit, right? So on its entire domain, it's continuous. Does this make sense? So they kind of skip over this issue of the limit as we approach negative infinity. And that's just because we really don't like to use limits in terms of infinity. But the point here is to say that we don't have any breaks in that direction, right? Does that make sense what I mean? Yeah. Cool. Awesome. So what about this case? This case is from -1 to 3. When talking about the continuity of this, you want to know if this is ever discontinuous inside this interval, right? We want to know if this is ever discontinuous inside of this interval. And then we want to know if this thing at 2 is equal to this thing is equal to the limit of this thing as we approach 2. Does that make sense what I mean? So what I'm saying is this. First notice, yeah, both functions are continuous. They're both parts of that piecewise function, they're both continuous inside those intervals, right? We agree about that. So g of x equal to 5 minus x, x squared minus 1, 2, x, 3. Negative 1 is equal to x plus equal to 2. All right. Question number 1. Try it a slightly different way. Okay. The first question we want to answer, like I said, is this thing continuous inside this interval, right? And we agree it is. Is this thing continuous inside of this interval? And we agree it is. Now the next question is, does this thing equal this thing at 2?
I can't really see the board.
Can't really see the board. Okay. I was afraid of that. Any better?
A little.
A little. Okay. Noted. All right. See video settings. Better?
Yeah.
Yeah? Dope. Awesome. All right. So like I said, the next question we need to ask is if these two functions or if these two pieces are equal at 2, if their limit would be equal at 2. From the graph, it looks like they might be, right? But we can't quite tell is 2 right here. So let's put a little button down. So from the left, we get that 5 minus x, the limit as x approaches 2 from the left is going to be 3. From the right, x squared minus 1 is going to be 3. So they do equal, so the limit does exist. We can say our function is continuous on our entire domain. Yep. What time is it? Okay, 12 minutes. Yeah. So, some new notation, a new type of function. It's called a step function. We have this function that really just rounds your number. That's all it does. And it rounds it to the greatest integer. So another way you might see this like that. And all you're doing is you're saying, let's round it up.
But you're running it down.
Wow, you're right. You're right, I misread that. We're using the floor function here. Good catch. So like I said, another way of writing it. And this is a bunch of different functions. One rounds up, one rounds down, and then one just rounds it to the nearest integer. So in this case, 3.9. We go to 3. In this case, 3.9. We go to 4. In this case, 3.6. We go to 4. 3.5. Go to 3. And this is just rounding it down. It's the greatest integer less than or equal to x. So if you had to guess, what would a graph of one of these look like?
So like the ones that like.
Yeah, it's kind of like a ladder or a set of stairs, right? The graph of these, would look something like this. The floor function, this, is just saying round everything down, right? The nearest value equal to or less than x. So if x was 0, the closest integer would be 0, right? Less than or equal to. At 1, again, just 1. But anything to the left of it would round down to 1. At 2 would be 2, but anything to the right of it would round down to 2. Make sense what I mean? So it ends up looking like this. Kind of like a ladder. Hence why they're called step functions. They look like steps. Okay. So what if we want to use them in a function? We need to find the limit. How are we going to do that? First, what would this function even look like? Well, this function would look like this, or replace it with, for now, just another x, right? It would look like that evaluated at just integer values, right? Does that make sense what I mean? Go to the graph, it'd be easier to show. So it's going to look like our original graph, like I said, just evaluated at integer values. You're going to get that stepwise pattern moving all the way through it. That's really all I have to say about that. But we see that we have a bunch of discontinuities, and that's why I bring it up now, is really just to be like, look, here's a great example of a function that it's going to inject a lot of discontinuities. It itself is super discontinuous all over the place, right? Having said that, I'm going to let you all out 5 minutes early today. I'd like y'all to go back and check this stuff out. Check out all the concept checks. For those who didn't see the email, the exam is being pushed off for next week. Just because I wanted to give you all time to actually digest all of this and ask any questions you might have during office hours.
What slide is this on?
Say what?
What slide is the concept of?
It's the very last slide. Also, there is a question of the week.
Thank you.